Okay, so today's lecture will focus again on estimators, and we'll introduce this notion of confidence intervals. Okay, so if you recall, we've been looking at this question of parameter estimation, and this is one of the basic problems of statistic. And the idea here is that we have this distribution D, which we know a form for this distribution, and we would like to estimate its parameters. Okay, so in this sense, D is unknown. So we saw two examples of this. In the first one, D was a Bernoulli distribution. So if you have binary data which only consists of zeros and ones, you can hypothesize that this data comes from some Bernoulli distribution. Recall that a Bernoulli is simply a distribution that is where a value drawn from this distribution is 1 with probability p, and it's 0 with probability 1 minus p. Okay, so we assume that this, so it's reasonable to hypothesize that data is drawn from this distribution, and our goal can be to estimate what this p is. So likewise, if you have some real value data, you can a reasonable model for this in many situations is what is called the Gaussian distribution or the normal distribution. And this is a distribution that has two parameters. One is mu and the other is sigma squared, like we've seen. And we'd like to find the best fit values for mu and sigma squared. Okay, so where best fit is in some informal sense, and that's the goal of estimation. Okay, so the goal of estimation is to find these unknown parameters of the distribution. Alright, so last time we saw this notion of estimator as being some function of the observations we have. Okay, so in all these cases, we'd like to perform estimation, which means we'd like to figure out the values of these parameters like p or mu or sigma squared. And the way we do it is that we have data and x1 through xn. Okay. And we said that these are what are called IID samples, okay, which means they are independent and identically distributed according to this distribution D. Okay. And an estimator using these samples is some function t of x1, x2 up to xn. And we said that an estimator is unbiased if the expected value of this estimator is equal to the parameter that we are trying to estimate. Okay. So the simple example we saw from last time is that we looked at this Bernoulli distribution. So if we have let x1, x2 up to xn be IID samples, from a Bernoulli distribution, with parameter p. Okay. So I'm writing this out so that you know how one writes this, right? So this is the notation. When we say a Bernoulli distribution with parameter p, we know that this I'm exactly referring to this distribution. So if you have IID samples from this Bernoulli distribution with parameter p, then the empirical mean, which is x1 plus x2 up to xn divided by n, is an unbiased estimator for p. Okay, and this is what we saw last time, and this is just a very fancy way of saying that expected value of x1 plus x2 up to xn divided by n when x1, x2 up to xn are all drawn from this Bernoulli of P, this is equal to P. So these two statements are equivalent, and note that if I say it in the second form, this is basically like a probability statement, and if I say it in the first form, then this is more of a statistic statement. And this is what I was talking about last time, which is that they're both saying similar things. It's just that in one we view that data is what is given and we are estimating this parameter, and probability you assume that you know what the distribution was and you are saying something about the data. Okay, but they're both saying mathematically they're saying the same thing. Alright, so this is the example we saw last time. Another example which we saw, which actually has, we didn't explicitly see it, but it has an identical proof, is that let x1, x2 up to xn be IID samples from a normal distribution or a Gaussian distribution. They're both the same thing, with parameters mu and sigma squared. Then again we have the same thing, okay, which is that x1 plus x2 up to xn by n is an unbiased estimator for mu. Okay, and this is the proof of this is the same as the proof of this, right, which is that you compute the expected value of this quantity, and so the expected value of this quantity by linearity of expectation, this would be equal to 1 by n times expected value of x1 plus expected value of x2 so on plus expected value of xn. Okay. And this, each of these is equal to mu, because these are all each of x1, x2 up to xn is distributed as a normal distribution with parameters mu and sigma, and by definition the expected value of the normal distribution is equal to mu. Okay, so each of these is equal to mu. Okay, so and we have n such terms, so we have the sum is equal to n times mu, and you have 1 by n over here, so this thing is equal to mu. Okay, so the n cancels out. Alright, so this therefore is an unbiased estimator for mu. Okay. Now suppose I ask, what is a good estimator for sigma squared? Okay, so that's the first question we're going to ask. Okay, so if you have data from a Gaussian, Gaussian has two parameters, one is mu and one is sigma squared. I told you that this quantity is an unbiased estimator for the mean, okay, which is mu. Now what is a good estimator for the variance? Okay, so that's the first question we'll try to answer. Okay, and what I'd like you to observe here is that you can also view this as an exercise in how do you deduce. So there's this meta question, how do you come up with estimators? right? Because for the mean, coming up with x1 plus x2 up to xn by n was a reasonable guess, right? So we said that if you're if you'd like to estimate the mean of a distribution and you had a bunch of samples, then the most natural one is just to try the average of the samples, right? So this is what is called the sample mean. Okay, and is there some analog that you can have for the variance, right? So that's something that we are getting at. But in general, you could ask this meta question: if I have some parameter of some distribution, how do I come up with an estimator for that? Okay, and so the answer for this is that it's usually trial and error. So the high level answer is trial and error, right? So what does that mean? So you guess an estimator and try proving it, and try proving that it is unbiased, or it has some low variance, or something like that. Okay. So remember, we saw what the notion of a variance of an estimator and the typical error of an estimator is in the last lecture. Okay. Low variance, low mean squared error. These are things that we saw last time. Okay, so the short answer is, yeah, usually you guess an estimator and you try proving that this is unbiased. Okay, so let's do this exercise for the case of the variance. Okay, so what is a good estimator for sigma squared, right? So let's write down. So if I have any distribution, we have a formula for the variance, right? So the variance of any random variable x. Okay, so by definition, so first, what is variance, right? So for any random variable x, the variance is actually the expected value. This is the definition of x minus mu whole squared, where mu is the mean. And last lecture and also before that, we saw that you can actually expand this out using the linearity of expectation, and you have this simpler in some sense formula for the variance, which is expected value of x squared minus mu squared. Okay, where mu is simply the mean, which is, note that, recall, mu equals expected value of x. And so I have expected value of x squared minus the expected value of x, the whole square. Okay, note that this is not 0, okay, because one is expected value of this quantity x squared. Here you are taking the expected value of x and squaring that term. Okay. All right, so this is a natural. So this is the definition of the variance. Okay. So now suppose I tell you that x is drawn from this distribution, which is the Gaussian, with parameters mu and sigma squared, then I know that this number evaluates to sigma squared. Okay. Okay, so for a Gaussian, this number evaluates to sigma squared. Okay. So now suppose I don't know the parameters of my Gaussian and I'd like to estimate them. Okay. Now this formula also gives us a hint for how to estimate them, right? So it's saying that I've got to compute, like I know that my parameter value, which is sigma squared, is equal to the expected value of x squared minus this expected value of x whole squared. Okay. So I could say I already know that there is a clean way to find expected values, right, which is taking the sample mean. Okay. So a guess for the for an estimator of sigma squared. Okay. So this could be expected value of x squared, right? So what would be a good guess for the expected value of x squared? So remember, now I am given the samples x1 through xn. Okay. So a guess for the expected value of x squared would simply be x1 squared plus x2 squared xn squared divided by n. Okay. It's the average value of x squared, right? So I take x squared at least over my sample and average it out. And I need to find this mu, right? So I've already estimated mu. So I said that x1 plus x2 up to xn divided by n is a reasonable estimate for mu. So this is supposed to be like mu squared, and this is supposed to be like expected value of x squared. Okay. So this quantity is simply a function of the data that you have, right? So this would be a guess for an estimator of the variance. Okay, so let's define t of x1 up to xn to be equal to x1 squared plus x2 squared by n minus whole square. Okay. So the reason I'm writing it like this is that this is now simply a function of your samples, right, x1 through xn. And it is reasonable to guess that this estimates the variance. Okay, so this likely gives a good estimator for sigma squared, right? Because we know that sigma squared is equal to the expected value of x squared minus mu squared, right? And I plugged in the empirical mean instead of this expected value. I plugged in empirical value for mu and the square of that. Okay. So the question is this an unbiased estimator? That is T an unbiased estimator for sigma squared.